Hello, explorers, and welcome to Reach the World's Explorer program. For more than 25 years, Reach the World has inspired youth to become curious, confident, and compassionate global citizens through virtual exchange. My name is Tim, and today we're journeying back to the San Diego Supercomputer Center to learn more about the amazing world of supercomputing, research software engineering, and the power of computers to drive discovery. Yesterday, we met Melissa Floca and heard all about her very cool work. And in just a minute, you'll meet Chief Technology Officer Rick Wagner for a closer look at what a supercomputer actually is and how one works. We may even get to see one. I'm very excited. If you haven't already read Rick's Virtual Exchange article, there's a direct link in the chat area. This will take you to the Virtual Exchange Journey homepage, where this and all future articles for this program will be published. I have a few more classroom shout outs to give before we get started today. A huge hello to Elliott Hine Middle School, Green Street Friends, United High School, PS1, Glenbard East High School, and Roger Quist Middle School. We're so glad you're a part of this program and going on this journey with us. If you're joining us via YouTube today, I'm excited to see your questions and comments for Rick. Please add them to the chat at any time and we'll fold them into today's event. And all of that said, I think it's time to welcome our very special guest, Rick. I will bring him on stage and say hello. Hey, Rick.
Hello. Hi, Tim.
Hey, it's great to see you. Thank you so much for joining us today. I'm very, very excited to journey back to the San Diego Supercomputer Center and hear from you. We've had a lot of fabulous discussions about what supercomputers can do, but I'm not sure all of our questions are answered yet about what a supercomputer is. So maybe we can start by just getting to know you and hearing a little bit about you and your career path, how you got to be working in such a cool place.
Absolutely. I'd love to talk about it. This is something that has excited me for many years. And to the point where I remember I was first talking to a professor that was teaching a physics class, and he told me about the work that he did in their lab. And to the point where I immediately followed up with his advisor and another professor, and it really started me down this entire path. But it took me a long way to get there. So, if you want to bring up the slides, I'd love to tell the story. So, welcome everybody back to the San Diego Supercomputer Center. We're sitting in the lobby. We're going to take a few minutes to go in there later, but right now I wanted to tell you a little bit about how I came to be working at the San Diego Supercomputer Center and what a supercomputer is. So Tim, if you want to go to the next slide. All right, so as Tim said, I'm Rick. And as much as I like supercomputers, I also like motorcycles. I've been riding since I was a kid. I don't remember a life not being around motorcycles. And I rode to work today, and I'll hope to be riding to work for the rest of my life. So next one. I like to try new things. That's probably a key element with a lot of folks that are in science and computing and others. This is me bungee jumping in New Zealand many years ago. I also was in the Army and I jumped out of airplanes. I'm not saying that this is a route you need to take, but it's an example of being willing to explore and try and experience is one of the things that'll make you say like, yeah, I can build a supercomputer or I can study physics or something like that. So next slide. And speaking of studying physics, I studied a lot of it. When I went to school here at UCSD, I began working in a research group that did simulations of astrophysics. And I was very interested in both the programming side and the physics side. And I first worked on what's called cosmology. So what you're looking at here in this picture is a simulation of galaxy clusters. Let me tell you what those are. So here I'm sitting on planet Earth, hopefully with the rest of you, or maybe not. Maybe some of you are somewhere else. But I assume you're probably here on planet Earth with us. And we have planet Earth, and we have our moon, and then we have our sun, and that makes up a solar system. And if you take stars like the sun, and you have a whole bunch of them, they form a galaxy. You've seen pictures of the Milky Way, which make a disk. Well, those galaxies will actually cluster and group together in large clumps, and those are the bright yellow spots that you're seeing. And then those structures will form along lines of filaments where all the matter that is collapsed down to make the stars and galaxy clusters make this web-like structure throughout the universe. So what you're looking at is a simulation of a really, really large portion of the universe. And this was the first thing I started to study, and it was more of a data science activity because I needed to help analyze this. I also like the fact that it made real interesting pictures. So Tim, if you can go to the next one. I also studied turbulence, and this is actually what I did my research in, because out in space, there are gases that move faster than the speed of sound. Now, here on Earth, this doesn't happen very often. We might have objects that move faster than the speed of sound, like a supersonic aircraft or something like that. And if you've ever heard the term sonic boom, that's the sound wave that moves along the Earth as the airplane is traveling. And that sound is so loud that you'll hear it below. And it's not just one boom, it's a continuous boom that goes along. Well, out in space, there's actually big chunks of air or gas. They're not as dense, they're very, very thin, but for space, they're dense, and they'll move along really fast like that aircraft, and they'll collide with other ones. And when those two gases collide, moving faster than the speed of sound, they stop moving. They just collide, and then gravity says, oh, time to do my job. And they collapse down, and they start forming stars, which leads to solar systems, which leads to galaxies, which leads to galaxy clusters. And so I love being part of seeing the initial process of how stars were formed. And again, it involved a lot of very large simulations and data analysis. So Tim, the next slide. And all of my research, everything I did to get my PhD involved supercomputers. This is an example of how we take those structures where we're simulating stars and galaxies and things like that. And you remember that web? Well, a lot of that web was empty. And when space is empty, we don't want the computers to do a lot of work. They don't need to. But where the bright points were, or where in the other simulation it was really dense where the gases has collided, that's where we need to form things along and have more detailed simulation of those lines. And so what we do is we do what's called a refinement. We have a grid or array where we've broken down our representation of the universe, and we make that much more refined in those areas. And then out in the open, we don't do it as much. And this is literally an example of those grids that we use. And this is how we take the work that we need to do and give it to the computers to do. So Tim, next slide. And eventually, I not only got interested in doing the science and using supercomputers, I started building. This is a team of us because, of course, it's not just me. I do my part when I was building them in terms of, whether it was networking or storage or systems management, and eventually I led the team that built and operated the computers. But it takes the people to have the vision. It takes the people to work with the users that are on board. It takes the people that understand how to get all the software working for the researchers and the security team and stuff like that. And of course, we're sitting in a data center, which is kind of like a machine room or factory that has to maintain and operate all of these systems. And there's a lot of energy and power and water and stuff like that that make it happen. And so, but that's how I started, was first doing that, where, doing them for research and then building them. So Tim, next slide. And of course, a supercomputer doesn't have to be as big as something that a team of us can stand by. Some of you might have heard of Raspberry Pis. Well, and if you haven't, Raspberry Pis came out maybe about 10 years ago, a little bit longer, and they're credit card sized computers that use the same kind of processors that we have in our cell phones, like the phone that's sitting across the table from me, because they have a lot of power. And if you can take those and put them together, you can build a supercomputer in the exact same way you would of one of these larger ones that's behind me. And so I had a team of students, and we got some Raspberry Pis, and we put them together, and we were able to run the same type of simulations and modeling and data science tools that we did on the larger ones. But of course, we had to do it at a much smaller scale. These small computers can do a little bit of the work, and so you would need a lot more of them. But they're really good for teaching people how they work. Of course, we found out they were really good for something else too. Tim, next slide. They're really good for playing video games, was what we used them for, because we took each computer, and I wanted to show people, how do you know what's happening on the computer? So if you can imagine playing a game like the Tron Light Cycles game, or a platformer or Pong even, which is an old game. Each computer would have a display showing what it was doing. It was responsible for one portion of the video game environment. And then as you played, each computer, each Raspberry Pi, communicated with each other. Where was the puck? Where was the motorcycle? Where was the little character going through the platform? And so we would take this to conferences like this one, and these are a bunch of undergraduate students going to college, playing video games because we were doing a competition, and I think we gave away a drone or something like that. So that's another thing that supercomputers are good for, is playing video games and teaching. So, good. Next one. So these days, supercomputers are developing a lot of, people are becoming very aware of them because they're being used to basically build the AI, the artificial intelligence models that are being used for things like ChatGPT and Llama and all these other tools. But of course, they don't always work perfectly. So this is an image that I tried to generate to share with some other schools about what a supercomputer looks like and what it is and what it does. So there's a term we use in computing, and that's garbage in and garbage out. And what it means is the programs and the machines and the software, no matter how good they are, rely on the correct inputs, and then they will give you the best output. So I think in this case, maybe I didn't give the best input to the ChatGPT as to what a supercomputer is. So I had to draw a picture. So Tim, let's go to the last slide. And let me tell you what a supercomputer is. And a supercomputer are just a bunch of individual computers connected by a very fast network. And what this means is that these computers communicate with each other and let them act as a single super, like the term superset, if you're familiar with that from math, a single supercomputer, because the performance as a whole starts to look like just a larger version of the supercomputer, the larger version of a single computer. Now, these days, when we talk about a computer, though, it's getting much more complicated because we have what we call CPUs, the central processing unit, and these are the things that you might have in your laptop or desktop or on a Raspberry Pi, and they'll do general computing tasks. They're very good for data analysis and certain types of problems. And then we have the term GPU, which is a graphics processing unit. Of course, nowadays, we don't always use this for graphics. We use it for working on long lists of numbers we call arrays. Because when you're playing a video game or in some other 3D engine on your computer, that's what the GPU is doing all the time. It's basically working on these large, two-dimensional or three-dimensional or n-dimensional arrays of numbers and computing them very quickly. Well, it turns out, in addition to video games, that's very useful for simulating things like stars and galaxies and earthquakes and fires and a lot of other stuff, and building AI models, which is why nowadays the way that we build supercomputers for research is the same way they build supercomputers for AI. Mm-hmm. So there you go. In a nutshell, that's what a supercomputer is. And if you want to do that, you don't have to jump out of airplanes or bungee jump or ride motorcycles. But I do recommend being willing to try new things and being willing to learn. So, Tim, if everybody's ready, I think what I'll do next is I'll go for a walk inside the data center. Now, it's going to be a little bit loud. So if it gets too loud, if you can just turn off my mic. But I'll go in there for a few minutes. I have to go through a door because we have security. And then I'm going to go walk behind one of our biggest supercomputers called Expanse that has liquid cooling and a very fast network and stuff like that. And I think it'll really show kind of how do you take all the slides and turn them into something we look at and touch.
Sure. I will move myself backstage so your screen is full screen, and we'll talk about what we see when you come back to the quiet area.
Okay. Then I'm going to flip my camera if I can. All right, now it just acts like, Tim, do you know how I can turn my camera around?
I'm not sure that is something allowable by this platform. Oh, there you go. You figured it out.
Did. All right. Let's go for a walk, everybody. So as I said, we have security requirements. And so to go in, I have to use this keypad, and no, I'm not gonna let one sec. Hey, pad's not working. Can you let me in? It's Rick. Thanks. All right. Oops. Okay. All right, and now you get to hear the noise. So, welcome to the front of the data center. This is some of the networking equipment at the very beginning. Now, one of the things we deal with here in California is earthquakes. And so we have these racks all on special bases that'll move in case of an earthquake. Another thing is you see these, that's where the cold air that comes up to cool the computers comes from. And then I'll show you now where all that air goes. So the warm air will come out from the rack and get pulled up into the ceiling. And then these large air handlers are ones that actually take the warm air that's coming down to the ceiling, cooling it using liquid, and it goes down along the floor to be brought up and fed into the computers on both sides. Which is why we use these partitions to make sure that the hot air stays in here and the cool air stays in its aisles. All right, it's about to get really hot and loud, so I'm going to turn off my microphone. Let's go look at a scan. Now, what I just showed you, those are some of the liquid cooling distribution that happens to those units down there. And then when I was turning inside, I don't know if you can see them very well, those yellow caps and the thick tubes that we saw there in, those are actually delivering liquid cooling to that directly to the chip. That's much more efficient than just using air, but of course you still have air. So that was Expanse. Expanse is a very versatile computer that's used by a lot of researchers funded by the National Science Foundation. And we have a lot of systems in here, and some of them are high security. So even though I had to use a code to get in, there's other computers that are isolated from just anyone from walking in and touching. They'll be working on research involving medical data or other things. And we have computers with lots of networking cables. That's the fast network that I was describing. And then here at the end, when I mentioned air handlers, this is our largest one. Inside of here are a bunch of copper tubes that run through, and the air comes down, and the cold water cools the air before it flows back out. Oh, that's funny. These are rear door chillers. You see these fans? They've got the same type of cooling distribution here of water. It's kind of acting, if you know about a car radiator, it's acting the opposite of that. And so it takes the warm air from the room, or the cool air from the room, pushes it through, and then cools it from here, because all of those CPUs and GPUs and the networking equipment get very, very hot. And you want to keep them cold so that they're very efficient and they can run as fast as possible. So, oops. Got to make sure I don't take a picture of what's going on in operation. So let me turn my camera back around. Hi, everybody. So I hope that wasn't too noisy. Let's go back outside and lobby. Oh.
Ooh, that was great, Rick. Wow, what a great tour.
I hope that you got to hear some of that, because there's a lot of just the fans and cooling. You have to move them really, really quickly to move the amount of air that's needed for those systems.
Yeah, that was maybe my first question, that it seems like a lot, besides the computing processors and the units for computing themselves, a lot of effort seems to go into keeping them at the right temperature, or at least an operational temperature. If there was no cooling, would the computers just get way too hot? Are they processing so much information, using so much energy, they would overheat?
That is exactly what would happen. They would basically shut down. And this is one of the big things when you're running data centers and you talk about efficiency. You want to spend the energy where you need to on the processors doing their job. But the processors generate heat. You need lights for people to see. So you've got to have ways to distribute the cooling and the liquid and turn on the lights and stuff like that. And so some of the electricity and power that you use doesn't just go to the processor or the drive or the network. And the less you can spend on running the system, the more efficient you are. There's another factor is this. Processors are electrical components, and those electrical components are more efficient when they're colder, not frozen, but cold. And so if you want the chips and stuff to work as well as they can, as fast as they can, you want to keep them cold. So using, sorry, I don't know how loud that got. Okay, if they're going to leave the door open, I'll need to move. That's the thing about this facility. It's an active facility. You see, like, you're in here all the time doing work. So you want to keep the processors as cool as possible, but you want to keep the amount of energy that you spend cooling the processors as low as possible.
I think as I move around the United States, and I know in more and more communities across the countries, data centers are popping up. They're a more common feature of our country specifically. Is there a difference between a data center like might be popping up, in a suburb of one of the cities our students live in, and a supercomputer center like you just showed us?
There's a few things that fundamentally, they're all very similar. You need a big room, you need enough electricity, you need some locks on the doors, you need enough power and cooling. And then it really gets down to what's different about them is, what is their purpose And then there's some other things about, like, for example, how much does power cost? So let's talk about power for just a moment, because this is a big deal. So like up in the northern part of Oregon, southern Washington state, there's a lot of hydroelectric dams. And so they can make power very cleanly, very efficiently, and very low cost. And so it's very appealing to put data centers there because they get this electricity from the hydroelectric dams and they put them there. Out in places like Wyoming, there's lots of land. And so, and also they've got some cold temperatures during the year, and so they can cool very efficiently. And so there's aspects like that in terms of where do you build a supercomputer center or a data center. Now, the other thing you get to is like, well, what's its purpose, right? Our data center, our supercomputing center was started 40 years ago when these things were very new. And so we've always supported supercomputers, and most of the computers you saw in there are used by researchers all across California, most of them here at UCSD in San Diego, but lots of researchers have systems here from some of the other universities. Whereas if you go across town into one of our suburbs, there's facilities where companies rent space where they might have a few computers or an entire rack. And then if you're somebody like Meta, Google, Microsoft with their Azure product, Facebook, all those others, they'll have entire data centers dedicated to just their computers. And so it kind of depends, one, where do you put it in terms of how much it's going to cost to operate? And then two, who are your customers? What's its purpose? And so you'll get different policies. Like here, we have a diverse set of systems, and it's more open because we do research. If you go to a Google data center, one, you're probably working for Google because they won't let anyone else in, and you're going to see things that are much more uniform and homogeneous.
Okay. You had pointed out early in your tour, and the audio was a little muffled, that the racks were able to move a little bit. And can you just sort of explain again why? Because I think that might be a novel concept for those of us who don't live in California.
Okay, so there's these things called earthquakes, and they can be very frightening events, but they can damage structures and other things that are attached rigidly. And so for those of you in New York, what you have is tall buildings with damping systems to deal with the wind and swaying and stuff like that. Here in California, what we have are what's called seismic isolation bases. Seismology being the term to describe the study of earthquakes. And there are these two plates that sit on top of each other. And on each plate, there are these two cups. I've got my hands kind of turned like little hemispheres, and there's a ball inside of them. And as the plates move, the balls push one cup up and lift the rack. So as the rack was sliding, like it would in an earthquake, it was also going up a little bit. So it's taking that energy from going side to side and lifting it. And then they put a little piece of like rubber or some other material that will damp or slow down the oscillation. So as I let go of the rack, it basically settled down back to its original position. They're very resilient. They can withstand very strong earthquakes. And if you look online, you might be able to find a video. There's a company called Sun Microsystems, and they took a shipping container and they filled it full of computers and racks. And they attached it to one of our shake tables where they study earthquakes. And they shook it, and they had cameras inside. And some of the systems were bolted down and some weren't. And so what was kind of amazing, one was frightening because you see computers flying across, is how many of them were able to stay operational in spite of the shaking. But that was the kind of research that led to seismic isolation bases to ensure that the computers are safe in the event of an earthquake.
All right. We got to see rows and rows. To my eyes, it looked like rows and rows of computers. Can you give us an idea of the computing power that you have at the San Diego Supercomputer Center? What is there a way to visualize or understand the power of your computer versus maybe the power of the laptop I'm talking to you through right now?
Actually, yes. A good way to think of that is our laptops are actually, especially the modern ones, are very powerful. They have their processors have very unique designs that allow them to use their GPUs or even now sometimes dedicated processors for running AI models. But a single computer, sorry, like when I showed the horizontal units in Expanse, that would be a single server. And there's typically somewhere between 30 to 50 of those in a given rack. And if we think about just an individual computer, it's typically somewhere between 2 to 10 times more powerful than your laptop. And so if we say, we have, 40 of those in a rack, and they're 10 times more powerful than your laptop, well, now we're saying that rack is 400 times more powerful. And then if we have 10 racks, it's 4,000 times more powerful than it. And it's actually more than that, because in addition to the processing power, it has access to, like, you might have a terabyte of storage on your drive. So gigabyte, and then 1,000 times that's a terabyte. Our storage systems typically start at the petabyte scale, which is 1,000 terabytes. And it has very, very fast access to the data. So not only can the computers talk to each other really quick, they can talk to large amounts of data to process it very quickly. And so thousands of times more powerful to start with. And then when you start adding them up, you start to get to 1,000,000 times more powerful.
Wow, that's very powerful. And for our young students who have grown up in a technology era where some of this terminology and this computing power is a little bit more normal, I have witnessed, and I'm sure you have too, a rapid development in this technology. Is it still developing? Are you still seeing, big improvements in this technology? Is it changing all the time? Or have we reached sort of a limit of some sort?
Oh, it is absolutely changing all the time. And that's the exciting part, is the continual advancements. And what's exciting for us, and also challenging for us, is, as you say, even young children and students are very aware of how things are changing. And that's driven more by the commercial and industrial side, right? The web, AI, social media, all the platforms and tools that we use are really what drives the architectures, the processors, the networking, the storage that we're now using for supercomputing. And it used to be the opposite. And so what it means is, when we're building something, we look at what's available and say, okay, of all of these products that are being developed to support things like TikTok or Google Drive or something like that, how can we leverage those for research and science? And so you mentioned your laptop, and I started to talk about how there's unique connections between the processor and the memory and the GPU and stuff like that. Well, our new system, Cosmos, has a processor in it that's very much based on a similar design to what you would have, say, in an Apple or Intel-based laptop. And so things are constantly changing. We're always figuring it out. And the work that the big companies have done, we call hyperscalers, have done, absolutely influences us, because they share their software that impacts the networking. And we may build things in different ways, but we're building with the same Legos.
Okay. We got to see yesterday some of the work that your colleague Melissa does using using the systems you maintain and design and build to solve problems related to wildfires and the prevention of wildfires and the maintaining or sort of reducing the risk of wildfires. If someone came to you with a problem like that, is there any sort of limit to what you can explore using supercomputing? Is there anything we can't do with supercomputers as they are now, but you think we might be able to do in the near future?
There are always limits. And these limits are really based on the fact that, like we used to tell this joke, I hope it translates. So we would model you saw a picture, right? I showed a picture of modeling the universe, all the galaxy clusters, right? And the joke we used to make is, even though we would model all the way down to the point where stars are forming, we didn't have a plug-in for dinosaurs, right? Is if you're modeling something at a very, very large scale, and you go finer and finer, and eventually you have from the galaxy cluster to the galaxy to the solar system where a star is forming, you can't eventually model the Earth. You can't eventually model the arrival of dinosaurs and something like that. So there's always a limit either in the amount of detail that you can have at the smallest scales or how big of something. So Melissa's work is very important and it can model fires at a certain region, but it's not going to be able to model all the fires on the Earth at the same time.
Mm-hmm.
And so we get closer. And one thing that we have gotten good at is how quickly we can model this. And this is where AI and machine learning really comes in, because when we're modeling these things, sometimes we have a good idea what it's supposed to do or behave, how a fire is supposed to spread, how an earthquake might damage a house, how a star might change its temperature and things like that. And if we can use a machine learning model to make that go a little bit faster, well, maybe we can use that to shorten the amount of time to do the simulation or the model or the analysis, which means that the people doing the work can get their work done faster because they're not waiting as long on the computer. So there will always be limits, but the first limit we usually fix on is time. And then the next one we start to improve on is scale. And if you've ever watched like some of the Unreal Engine videos where they're showing how quickly they can generate the 3D scenes people can view inside a game in near real time, that's the kind of improvement that we see in scientific applications as well. We do increase the detail, we do increase the scale, but eventually you just run out of what you can do.
Okay, and as the person who sort of designs and builds and maintains the supercomputers at the San Diego Supercomputer Center, if something's going to break, what's it going to be, and how would you fix it? What's the most common sort of technical challenge you come across?
Well, the first one is that the human beings, because the first thing that happens is it's usually the people that are using the system. Even if everything is fine on our side, right? The network is fine, everyone can connect to it, the computers are running. We're still teaching people and bringing on new people to learn how to do supercomputing. And even when somebody's very experienced, they want to push these boundaries. They want to do something bigger and better and faster, et cetera. And so the first thing that usually goes wrong is somebody pushes the system beyond its limits. And that's why we have these systems, is literally for people to find the boundary and try new things. It's the bungee jumping analogy, right? It's so the number one thing that we deal with is people coming on board and reaching the limits of what they can do. And the system basically says, I can't do that. And then we step back and we work with them, or they figure it out and they say, okay, can I do it a different way that does make it go faster? And then the next thing that usually happens is it's usually the network that we pay the most attention to, because everything is dependent on the stability of the network. Everything we just said, the computers need to be able to talk to each other, they need to reach the data, people need to be able to come in and launch their jobs and stuff like that. They need to be able to run their analysis. The network is critical. And we're just fortunate that we have a lot of good people. Like I don't have to spend most of my time worrying about how well that system is running, because there's a lot of smart people that have put time in making sure that it does work well.
Excellent. We've learned a lot, and we'll learn more about the research software engineers who sort of take the power of your computers and apply them to these interesting scientific questions, and make them really useful tools for researchers and scientists. Are there any questions currently being sort of investigated through this unique connection of powerful computers and really useful software engineer or research software that get you excited, that make you just like excited about what you're going to discover?
So I have a very pragmatic side. One, I'm very happy that the community has identified research software engineering as a role, because this is very much a team activity, whether you call it a team sport or a team job or whatever it is, because people can only, in the same way the computers have limits, people have limits. There's only so much they can be experts in. And if you want the best, it's better to have somebody who comes in with the ability to do the software development for a research project. So you can have scientists that are even better at doing the science, and then you can have systems people that are even better at building the systems, and they'll overlap and they'll share experience. but you get to bring these expertise together. So that in itself, as far as the human and social aspects, is really important. And then the thing that I've been excited about is that research projects are sort of like small businesses or small nonprofits or whatever, where you don't want them to take on any more burdens than they need to, right? It's basically how much can they do applying just their scientific knowledge without having to run a supercomputer on their own. Well, we already operate it, so that's taking off one burden, but now can the software side do more for them so that they can ask their questions with doing a little bit less development, without having to run their own web servers, without having to run their own storage systems in their research communities. Basically, the more operational aspects that can be handled by the community, by a supercomputer center, by their university, so that they can focus on the science, that's where I'm trying to push the technology. It's not as exciting as AI and stuff like that, but on a day-to-day basis, it's researchers shows up to do their job and they're not worried about some technical thing breaking. They're only worried about the science question. That's what I want to get to.
Excellent. I have two more questions for you before we wrap up. We talk a lot at Reach the World about explorers and exploration and being curious about the world around you. Do you feel like you're an explorer in the work that you do?
Literally. If I'm not constantly aware of some aspect or some part of our community and research ecosystem and technological environment, I'm not able to contribute. So I'm both an explorer by nature, and exploration is part of my job. That same way I mentioned the researcher who tests the boundaries to find out what the system can do and how to make it go faster. That's inherently what drew me into research in the first place, and wanting to push computers to their limits and maybe a little beyond occasionally, since we can do that.
For final question, for all the students who are following along and will watch this event and think, wow, that job looks really cool. I love playing video games. I love playing on my phone. Love you asking ChatGPT answers and seeing what it will give me back. What advice would you have for kids who really, really enjoy being around computers, thinking about computers, solving the sorts of challenges that you've described over the last 40 minutes?
So it's sort of like why I like working on computers. It's the analogy, the story I'm going to tell is I love to read books, but I don't like to write books. And so I didn't become an author and I didn't become an editor because I like to consume them. But as far as the production of literary content, it's not my thing. Now, computing, I do like video games. I do love seeing, Enter the Spider-Verse and stuff like that because I love the animations and stuff like that. And I know the computing power that we need to. But in addition to that, I like to get my hands dirty, right? And so my advice to folks who want to decide, are they interested in the technology because it entertains them or it satisfies them? If it's a passive activity, like the same way I read books, that's great. Enjoy that. That's part of what you do at whatever level. If you want to go further, you've got to start tinkering. You've got to start building either actual systems, putting computers together or other devices and things like that, or using software. Like I got to mention Roblox, right? Roblox Studio. You can start writing your own games, and that'll get you thinking programmatically. And you can think about like, how do I build a quality game? What does it mean to build a quality game? And how do I implement that in code? Or if you're working at home and you want to get different devices talking to each other. So this is how you go from being a consumer of an activity, which is very valid. I consume lots of media, I enjoy it, to being somebody who produces it, modifies it, creates it, is finding the area that most interests you and trying it out. So it's going from one side to the other, and being very deliberate in your choice.
Well, I think you made a lot of students really happy saying that maybe there's a place for Roblox in their classroom. So you got a lot of new fans, Rick, and it's been fascinating talking to you today. Thank you so much for the wonderful tour. It was great to see everything you've got going on over there, and we appreciate the fact to see what a real supercomputer looks like. So thank you so much for being with us today. I want to say thank you to our students and our teachers and schools for joining us today. Keep looking for new articles on the Reach the World Journey homepage. The link to those articles is already in the chat. just give it a click and check it out. Rick has a wonderful article there if you haven't already seen it. And after you read all of these articles with your class, you'll always have the chance to meet even more experts like Sandra, Melissa, Rick, and others in the weeks ahead. So I'm, again, very glad to be on this journey with you all. We're going to say goodbye to the San Diego Supercomputer Center for the time being, and keep exploring, everyone. Thanks again, Rick.
Bye.